Yeah, I mean, yeah. This is one of the highest scoring quizzes I've had this semester. Must be because the ones that don't understand the material don't show up, you know? But all right, so okay, convolution, you should just be able to convolve two signals, nothing that deviates from the past. Impulse response, you should know what the impulse response is. So just remember that when you assume that the impulse is a delta function, that's called the impulse response. And if I take the Laplace transform of the impulse response, I get what's called the transfer function. Additionally, for impulse response, we know that the output is the convolution of the impulse response with the input. So that's why it's important. And in the Laplace domain output is just the product of the transfer function with the Laplace transform of the input. So that's what you need to know about impulse response. At this point, you should be able to solve circuits, first and second order circuits, with zero and non-zero initial conditions, whether you only use Laplace techniques or use the differential equation techniques. I don't really care. You just need to know how to solve them. There's going to be a few examples on the exam on this. In terms of transfer functions, so you should know how to compute a transfer function. So it's just the ratio of the Laplace transform of the output to the input. You should know how to use it to determine the response to any input, and then know how it's related to the impulse response. Finally, you should know how to use this transfer function to determine stability, what the poles are and the zeros. So basically, if you have any poles that are negative, your system, or zero, or purely imaginary, your system is unstable. What else is there to know? That's pretty much it. After that, we started evaluating the frequency, the transfer function on the imaginary axis, and we called that the frequency response. And so you should know how to draw these frequency response plots, determine the order, and also you should know how this frequency response is related to the steady state solution. So does everyone know how it's related to the steady state solution? So basically, h of j omega cosine omega t plus the angle of h of j omega is the steady state response due to an input cosine omega t. So you should know this. It will show up in the final. What else? Finally, you should know how to magnitude and frequency scale circuits. We went over that yesterday. And then we started talking a little bit about filters. For filters, for the second order filters, you just need to know kind of all these parameters, the quality factor, the bandwidth, omega low, omega high, HM, and then how to extract them from a plot. So remember that if you have a series RLC, the maximum response is actually 1 over the resistance, because the maximum current that can be fed into this circuit is when you're at resonance, basically. So you should know all these things, basically. Also, you should know how to convert from decibel to linear. So if this plot is in decibels, before you can read off the resistance, you have to convert to a linear scale. What else is there? Relevant parameter. yeah, so that's basically it. Identify normals. Yeah, so you should be able to identify normalized Butterworth filters. So basically, if I give you a circuit, you should know whether it's low pass, high pass, band pass. That's going to be very important for the final. So by looking at a circuit, what the input and the output is, you should be able to know what kind of filter it is. Finally, you should be able to design low pass and high pass filters using the methods that we described in class and how to design low pass active filters. For my section, you just have to focus on the parallel resistor configurations. The Sallen-Key configurations won't be in the final. So that's basically all of it. And additionally, we learned about NMOS and PMOS transistors. So in particular, at this point, I want you to be able to solve DC bias circuits. So I would focus a lot on that. And you should also know all of these plots, like when you have ID in the y-axis, VGS in the x-axis, or ID and then VGS and VDS. And then this is a pause. So from this plot, wait, sorry. Yeah, from this plot, what kind of transistor do you think we're looking at here? This plot here. Is it N or P type? 3. So you just have to remember that for N-type, as you increase BDS, the currents increase. And so this is an N-type transistor. You should know that this is saturation, this is the triode region, and then this is whenever VGS minus V threshold equals VDS. What other regions of operation are there? Yeah, so that's kind of you should be able to identify based on these ID curves. What else is there that we learned about transistors? Finally, there is going to be one small signal question. So if I give you a circuit, you should be able to either extract the R out, R in, or the gain of a single stage amplifier. The circuit will be very simple, but you will have to do this. This won't be in your final if you're in West Lafayette. And also this kind of will be in your final because we're going to be looking at active amplifiers, but I won't directly test op amps because that requires you to know how operands operate already. So this also will not be as its own standalone topic, but you do need to know it in order to be able to be successful with the active circuits. Are there questions at this point? No questions. Okay. Skip this since I said it wasn't. Convolution. Yeah, so for convolution, you should just know kind of how to apply a convolution to a function. And in particular, in class, we spent quite a bit of time doing examples of the form u of t minus tau. And this, of course, translated to use of t, the integral from 0 to t dt. Now, we also learn a special trick later on in class, which is that I can just take the Laplace transform of f of t, multiply with the Laplace transform of g of t, and then take the inverse Laplace, and that's going to give me the convolution of the two. So in your exam, you might be able to get away with this and then avoid doing a lot of this. In practice, believe it or not, almost nobody uses this formula. What they do is this, because it's much more computationally efficient. You need to understand this formula more so that you get kind of the mechanics of what's going on when you convolve two signals. Yeah, so like I said, there's also multiple ways to derive the impulse response. We learned kind of one method, which was first solve for the unit step response. So basically assume that your input is a unit step, find the response, take the derivative of that, and that's your impulse response. Later on in class, though, we also learned a better method of doing this, which is to solve the circuit in the Laplace domain, assuming that your input is a delta function. And in the Laplace domain, a delta function becomes a 1-volt source. And so it becomes very easy, and you can assume zero initial conditions. You just need to know one of them, because to find your impulse response, you can use either one of them. Questions, concerns? All right.
How do we do it in the Laplace? The impulse response?
So let's say you want to solve, to find this impulse response, you would want to solve this circuit in the time domain, which you can't really solve using the differential equation way, because this doesn't make any sense as a source. But in the Laplace domain, say this is R, and the circuit that you're solving to find the Laplace domain is so let's say my output for the circuit was I out, then my impulse response would just be, I out would actually just be 1 over R plus 1 over SC. So that's going to be my transfer function, H of S. I can just inverse Laplace this, and then that's going to give me my impulse response. Does that make sense? You could also just basically solve another circuit where you say that this is U of t, come up with the response, take the derivative, and then that will give you the impulse response for this circuit. Either way will work, but at this point, I mean, I think this is a much more straightforward way to do that. Okay, yeah, so Laplace transforms. Yeah, so this won't be emphasized too much, but you should be able to take Laplace transforms of a function like this one. So for this particular case, since there's a unit step function that's shifted by 1, you need to shift every time by 1. So basically you have t minus 1 e to the negative 3 t minus 1 plus 1 or minus 3. And then u of t minus 1 plus u or plus 1 e to the negative 3 t minus 1 minus 3. So then you're going to get that this is just e to the negative 3 times the Laplace transform of t minus 1 e to the negative 3 t minus 1 u of t minus 1, and then plus the Laplace transform of e to the negative 3 e to the negative 3 t minus 1 u of t minus 1. And at this point, you can use the time shift property along with these two to get that this is just going to be e to the negative 3 e to the negative s 1 over s plus 3 squared plus 1 over s plus 3. Is that clear to everyone? Yeah, so basically you should kind of understand some of this stuff. There won't be a lot of this kind of stuff, but it's good practice to know how to use these tables effectively. What is the output? Okay, so if a system has an impulse response of h of t of this, what is the transfer function? Yeah, so it's just going to be h of s equal to 1 over s plus 1. And so if this is the input, the Laplace transform is going to be, of the input is just e to the negative 2s times 2 over s, because we have to shift by 2, and then this is the Laplace transform of u of t. So what is the output? Well, we just have to find the inverse Laplace transform of e to the negative 2s, or 2 times that, 1 over s plus 1. Okay, well, how do we find it? Well, this just tells us that it's going to be delayed by, whatever our answer is, needs to be delayed by 2. And we need to basically do partial fraction decomposition on this. This is actually fairly straightforward to do partial fraction, so I'm just going to add s and subtract s to the numerator. So I'm going to get that this is just 1 over plus s minus s plus 1, which of course is just 1 over s minus 1 over s plus 1. Okay, so now that we know that, well, we need to take the inverse Laplace of 2l to the negative 1, e to the negative 2s, 1 over s minus 1 over s plus 1. And then basically we're just going to get that this is just 2 u of t minus 2 minus 2 e to the negative t u of t minus 2. That's it. That's our answer. Yeah.
How would you get from 1 plus s minus over s plus 1 to 1 over s?
Oh, so these first two terms cancel the s plus 1 factor, so you end up with this, the first term, and then the last term cancels out the s, so you end up with this. Of course, you could have done like the way that I kind of taught you how to do it, which is basically multiply by s and evaluate at 0, which is going to give you 1. There it is. And then multiply by s plus 1 and evaluate at negative 1, which is going to give you negative 1. There it is. I just did this one by inspection. So you know that if I say a0 over s plus a1 over s plus 1, according to our little formula, a0 is just going to be s over s plus 1 evaluated at s equals 0, which is just going to give me 1. And a1 is just s plus 1 s plus 1 evaluated at s equals negative 1, which is just going to give me negative 1. And that's what I basically got here. So you could have done it the formula way that I gave you in class, or just kind of winged it, basically. Questions about this? So I can guarantee you this kind of thing will show up. I'll give you either impulse response and give you an input, or I might give you the unit step response, in which case, what do you have to do to the unit step response to get the impulse response? Yeah, so then you're going to have to take the derivative, and then you can do your thing, basically. So just be careful in the exam, because you might get a unit step response, and you have to know what to do with that. Okay, so here it is. Now, you could have done this the old school way. If you're like a pioneer engineer and you want to do things the hard work way kind of way, and you could have just taken the convolution between, and you would have gotten the same answer. So that's another way. So you could have just said that y sub t is just equal to the integral of e to the negative tau u sub tau times 2 u sub t minus tau minus 2 d tau from negative infinity to infinity. And then after a lot of rationalizing, you would have realized that this is just the integral from 0 to t minus 2 e to the negative tau d tau, and then you get a use of t minus 2. And then you would have basically done this integration, and then you would have gotten 2 e to the negative tau negative evaluated at 0 and t minus 2 use of t minus 2, and then that would have given you 2 negative e to the negative t minus 2. Sorry. Yeah. Plus 2. And then you have to multiply this whole thing by use of t minus 2. So you could have also done it this way. And as you can see, I hope I got the right answer. Let me look in the next slide. Yeah, and then you get the same answer. So it doesn't really matter. Both ways work. Okay. Yeah. It's important that you know how to analyze these circuits. You should know also what critically damping means. So when your solution looks like this, it's critically damped. When your solution looks like this, and where your roots are imaginary, it's called overdamped or complex. Sorry, when your roots are completely real, it's called overdamped, and then underdamped is when they're complex, and then undamped whenever they're purely imaginary. So you should definitely know all this. I might ask you, like, this circuit here is currently underdamped. What do I have to do to R to make it critically damped? And so you should know I need to increase R in order to make this critically damped. So you should know what these classifications. What else is there? Yeah, so that's, I think, basically it. So you should know what the impulse response is. Remember, it's just the ratio of the input to the output. Or another definition is what the output is whenever your input is 1. So you could either define it as the ratio of the output to the input, or what your output is when your input is 1. Of course, if your input is 1, the ratio is the output. So I'm just saying the same thing in a different way, basically. There's no magic there. What else is there? So yeah, you should know that these are called zeros. These are poles. And you should be able to infer the order of a pole or a zero based on looking at your frequency response graphs. And what else is there? You should be able to infer stability based on the location of the poles. So remember, a pole that has either a 0 real part or a or a positive real part leads to an unstable system. Either 0 or positive, unstable. Negative is stable. Okay, so what else is there? Let's see. Yeah, so Yeah, that's pretty much it about this. So your resonant frequency is just basically the frequency where the impedance or admittance is 0. Sorry, the imaginary part of the impedance or admittance is 0. In which case, for all of these circuits, it would mean that these two, their impedances cancel each other out. And so in this case, you end up with an infinite response, and that's why the response for this circuit looks like this. And as you increase resistance, it becomes flatter and flatter and flatter. Yeah, so that's basically resonance frequency. Bode plots, so just remember, if you have a 0 at 0, depending on how many, you're going to start with a positive slope. If you have, each time you cross a pole, so your slope decreases by a factor of 20 decibels per decade, or it moves by negative 20 decibels per decade. And every time you cross a 0, it increases by a factor of 20 decibels per decade. So that's basically it. What's next? Also, very important, if you have an input at omega naught, from these plots, you can actually read out what the steady state response will be. So basically, if I told you for this particular plot, although we don't have the angle, let's just assume like the angle of h of j 100 is 0, or it's 10. And then I told you to find the output whenever the input is cosine 100t plus 30. Then you would know it's just the steady state would just be, I would just have to look at here what happens at 100. And I'm at negative 80 dB, which remember in a linear scale is actually 10 to the negative 80 divided by 20, also known as 10 to the 4. So I'm just going to multiply this by, to find my steady state, I'm just going to say that the steady state is 10 to the 4. 10 to the 4 cosine 100t plus, and I just told you that the angle was 10, 30 plus 10. And that's all you need to do. Now, if I had given you a plot of the angle, and it looks something like this, and then here it's at 10 degrees, and then here it's at, 100. Then you would have just read the 10 degrees, and that's what you would have written there. Okay, cool. Yeah. So we went over this yesterday, but basically if you want a frequency scale or magnitude scale, a circuit, to magnitude scale, you multiply all impedances by Km. So in the case of the resistance, you multiply by Km. In case of the inductance, you multiply by Km. In case of the capacitance, you divide by Km, because remember that the impedance is proportional to 1 over C. And so when you multiply that impedance by Km, you divide the capacitance by Km. Whereas here, the impedance is proportional to R, and here the impedance is proportional to L. What I mean by proportional, well, the impedance is SL, and here it's 1 over SC. So when I multiply this impedance by Km, the resistance becomes KMR. When I multiply that impedance by Km, the inductance becomes KML. And when I multiply the capacitance by Km, it becomes Km over C. Now, remember, we also talked about frequency scaling. And to frequency scaling, since you're trying to do something with the argument S, and R is not dependent on S, you don't do anything to R. Now, with respect to both the capacitor and inductor, since you're replacing S with S over KF, and the S is always multiplied with the lumped element parameter, whether it be that capacitors or inductance, whenever you frequency scale, you divide the inductance or the capacitance by KF. So that's what you do to the actual circuit, and this is what happens to the transfer function. In the argument, whatever S you had got divided by KF, and in the outside, depending on the units, the transfer function will get scaled. If it's unitless, nothing will happen. If it has units impedance, it gets multiplied by Km. And if it has units 1 over impedance or current over volts, it gets divided by Km. So that's frequency and magnitude scaling. In the past, I've done this. I don't know if I did it this exam. I might have done it. You never know. I give the students H of S equals 1 over S plus 10. It was a little more complicated than this. I mean, I'm not that nice. But but the spirit was the same. And then I put here S. And then I asked them, what happens to this transfer function if I frequency scale the circuit by 10? And all the students had to do was H of S equals. This was a free response, and oh my God. This is what I wanted to see, but it's not what I saw. Because some students decided to cancel the 2 10s out. Another set of students decided to kind of multiply out this 10. Another set of students decided to do something else. And so it took me a really long time to grade this. And then which I'm kind of basically giving myself out. I'm reluctant to give questions like these after that because it was a pain to grade. It's like a million correct answers and I don't have time to look for all of them. But anyway, the whole point was that all you had to do was realize that when I frequency scale, I just take my S argument and I divide it by KF, and that's it. That's all I got to do. Of course, because there's a square here, I have to divide by 100 because there's 2 S's there, basically. And that's why you put everything into the little parentheses and then you're fine. Okay, so that's all I have for magnitude. Again, for these, you have to know all of these parameters. I would put them in your formula sheet or whatever. And that's it. Okay, so for low-pass filters, just remember that we start from a normalized low-pass filter. So all of these filters here have a frequency response H of j omega, which is equal to 1 over omega to the 2n. And in order to design our low-pass filters, we need to pick 2 things. One is how big this n has to be, which translates to how steep does the slope need to be in order for us to make the transition from the pass band magnitude to the low band magnitude. Now, to give you an idea of what I mean by that is, if my stop band was defined as being like right here, I could just basically have a filter that very slowly transitions, so I would need a much lower slope than if I put my pass band here. Well, my filter has to go from this amount to this amount down here in a very steep kind of way. And so, sorry, I wrote this wrong. Hold on. Yeah, eraser. Okay. So if my stop band was down here, somewhere like really my H min was way down here, or A min was way down here, I would have to basically go from here, which is where my passband ends, all the way to down here in this transition region very rapidly. And so I would need a much bigger slope, which translates to a higher order. And so my 2 design parameters are how high an order I need or how big of a slope I need. And then the other one is how much do I have to shift this normalized design to the right in order to be able to get so that my passband, so that my response is higher for all of the passband and lower for all of the stop band. So kind of, I need to first figure out how big does the slope have to be so that I can have my response fall fast enough within the transition region. And then the second thing that I need to figure out is how much do I need to rescale this circuit so that it like fits in the correct location. So the blue line is the normalized circuit that I chose that has the correct slope in this figure. So if you notice, these two have the same slope. So that's the response of one of these circuits, which are all normalized so that their cutoff occurs at 1. And then to design it, then I just have to basically frequency scale this blue circuit so that my cutoff now sits at omega c. How do I make my cutoff sit at omega c? Well, originally this is the frequency response. And you notice that when I plug in for omega 1, I get 1 over the square root of 2, because 1 over the square root of 1 plus 1 is just 1 over the square root of 2. Well, if I want my new cutoff frequency to sit at omega c, I can just take that omega and divide it by omega c. And now when I plug in omega for omega c, I'm going to get 1 plus 1 in the denominator. So I'm going to get 1 over the square root of 2, which is also known as the new cutoff frequency. So what I'm going to do to this design is I'm just going to frequency scale it by a kf equal to omega c. Does this make sense? So first step is figure out what slope is, what set of filters will have a steep enough slope, which means figure out the minimum order filter I need. As I increase the order, the slope will increase by a factor of, by a factor of negative 20 dBs per decade. So first order filter will have a negative 20 slope, a second order will have negative 40, third order negative 60. And that's because I'm gonna have 3 poles creating that slope, or 4 poles, and so on. Once I pick that slope, I just need to basically pick a base circuit that's normalized, and then I have to figure out how much to frequency scale it to get my correct circuit. And that's basically my design process. So that's kind of what I do. To design a high-pass filter, I'm going to use the fact that I know how to design low-pass filters. So I'm going to convert all of these design parameters into a equivalent low-pass filter design by using the following transformation. Capital omega, which is in my low-pass filter space. I'm going to call that low-pass filter space, as omega p over omega. So in that case, capital omega p is just 1, or omega p over omega p. And then capital omega s is just omega p over omega s. Once I have these, I'm just going to design a low-pass filter to meet those specs. And then once I have my low-pass filter design, I'm going to convert it by replacing all my capacitors with inductances and inductances with capacitances. And this is the correct values of capacitances and inductance. Are we good there? Yes, no, maybe. All right, that's it. And then active filters, we went over that yesterday. Yeah, let's look at some examples. So let's just assume the circuit closes at 0, not open. So in the figure it shows it opening, but we're going to assume that it closes. So what would be the initial inductor current? Can anyone tell me? If this circuit has been open for a very long time, it's been disconnected, well, how much current do you expect there to be? What? Here, I'll draw it out. So t less than 0. We have 4 ohms, and then we have this inductor, which after a very long time behaves like a short, and then a 10 ohm. How much current would be flowing through here? How much current flows through an open circuit? Yeah, so this is an open circuit, so I's of 0 minus, which equals I's of, or IL 0 minus, which equals IL 0 plus, equals 0. And then What else is there? Okay, so now we have our initial condition. Now we have to solve for time greater than 0. We have to basically solve this circuit. Now, at this point, I could tell you, you could solve this using our good old differential equation techniques, but at this point, we have some better machinery. So we can actually say, convert this into the Laplace domain. And so we will have, so this is actually 12u of t. So we're going to have plus minus 12 over s. And then here we have 4. And then 0.1 s. And then 10. And then we need to basically figure out how much current is going out through here. IL, so S. Well, this is just a current divider. So we basically just need to figure out what total current is coming out. So, and then figure out how much of that current will end up here. So the total current coming out would be the voltage. Or is that is there a better way to do this? Yeah. 12 over S divided by yeah, 4 plus 1 over, what is it? 1 over 0.1 S plus 10. And then, so this is just this in parallel with this. And then I can multiply that by this in parallel with this. 1 over 0.1 S plus 10. And then to get the amount, so that's going to give me the amount of voltage drop from here to here. And then I need to basically divide this whole thing by 1 over 0.1 S in order to get the current. And that's going to be my final result. Now this looks more complicated because I'm not very good at solving circuits. But as you can see, this will cancel this out. So you're just going to end up with a 1 here, and then you have this 4 multiplied by that. So things actually algebraically clean up. Here's the equation I wrote on the previous slide for V sub S. And then, wait, what's it asking for the voltage? Oh, it was asking for the voltage, not the current. Okay, so forget about multiplying by 1 over S. Okay. So here's the expression for V sub S. Then you can do some algebra, and then you can get it cleaned up to this, and then take the inverse Laplace, and there's your circuit solution. Once you know the output voltage or the voltage across here, V, in order to find I, you can just basically use the relationship, which is that VL equals L ddt of IL. So you can invert this relationship in order to get your final solution. Does this make sense? So you should be able to do all this stuff for the final. Yeah, so you can practice this at home. Okay, so this is an interesting one. So if you look at this plot, assume that it is showing you the inductor voltage. And then you're told that V0 equals 3. And the inductance is equal to 1. What is R? So how would you tackle this problem? So this plot here, it's e to the negative r over lt. And so this is when it's fallen by basically e to the negative 1. So that tells you that 3 is actually r over L. And since you know L, that gives you that r has to be equal to 3. So that's basically what you would do for this kind of question. Makes sense? Let's just skip this. Some more practice you can do at home. Okay, if I told you that this plot was on the linear scale, and I told you that this was the circuit and the output is V out, what would be the resistance for this particular circuit? What is the output V out? So it's I in times what? Well, times the impedance, yeah. So the impedance of j omega. And at the maximum, it would just be I in times R. And so V out over I in, the frequency, what is the frequency? J 1 over the square root of LC is just going to be HM, which is also equal to R. And so what is the resistance? Yeah. That's for the series. Or I might have said it wrong, but that's for the series where you have basically R, C, and let's say L, and then you have a voltage source, and then your output is the current, which is kind of the frequency response is 1 over the impedance. Okay, so that's 5. And then since you know what L is, how could you use that to figure out how could you use this graph to figure out what C is? So where does HM occur? Yeah, which is the resonance frequency. And so you know that 1 over the square root of LC is equal to 2. And since I gave you L, you should be able to find C. Then the rest, I mean, you can just apply a formula to find them, but...
Again, where do you find the R?
What is the maximum response you can get out of this circuit? What frequency? Yeah, and at resonance, the impedance is R, and the output is the voltage times, the resistance, or the impedance times the current. So as a result, that's how you know that R is the maximum in that graph. Go ahead.
Do you have to break out the quality graph here?
I mean, you should know how to compute it, but I mean, you have a formula sheet, so maybe. So you just need to know it's omega m over the bandwidth. Okay, what else is there? So let's say I gave you this circuit here, and I told you to rescale the circuit to get the response in the bottom. This is important. What's the first step that you would need to do that? Yeah, so we need to basically figure out what is Km and Kf. So one way to do that is you have to realize that h of j omega, right, will become, well, first of all, what are the units of the input and the output? So this is supposed to be a what do you call this? A bandpass filter, because it's so it's V out. So we have, what are the units of the input and the output? V out over I in, which is also impedance. So what is Km, huh? Well, if you look at these two graphs, this one, it has a maximum that's 10x bigger. And since the graph is in units impedance, we know now that Km equals 10. Now, to figure out Kf, there's kind of, it's a little bit more tricky because, so what you can do is if you look at what happens at 1, and then you identify on this graph where 1 is, well, that's where Kf over, when you plug in Kf to this expression, you get Kf over Kf. So this is Kf. Now, you could have also looked at where Hm occurs. So initially it occurred at 2. In order to get 2 here, I have to plug in 2 times Kf as my argument for omega. So that tells me that this 80 is actually 2 times Kf. And so in order to get Kf from this data point, I would have to divide it by the value on the x-axis on the original graph. So there's 2 ways to identify this. You either stick to always looking at what happens at omega equals 1, and then look at the other graph and figure out where does that occur. Or you can look at any point, but then you have to realize that you have to divide by the magnitude of that point. So kind of like omega new divided by omega old is Kf. In this case, this is the omega new old, so this is where the maximum used to occur. This is where the maximum now occurs, so the omega new. If you take 80 and divide it by 2, I'm going to get 40, which is the correct Kf. I can also just choose 1 here, and then I can choose 40, and so basically it's going to give me that omega mu over omega old is just 40 over 1, which is just Kf. Okay, now that we know all these things, what do we have to do to the inductance? Yeah, so we multiply by 10 and divide by 40, and so we're going to get 1 over 4. The resistance, we just multiply by 10, so we're going to get 50. And the capacitance, we are going to both divide by 10 and divide by 40, and so we're going to get 1 over 1600. That's it. And I guess I only did, what? Oh, there you go. Yeah, it's just not very neatly written, but it basically, you multiply by Km and divide by 40 for L, you multiply by Km for R, and you divide by both Km and Kf for C. That's it. Okay, if I showed you this plot, based on looking at the slope from here to here, so we move 20 and 40 decibels, is 10 to the negative 1. So we moved about 20 decibels per decade in the positive direction. How many zeros do you expect there to be at 0? Yeah, exactly. So this thing probably has a transfer function of S. And then here, the slope becomes bigger by how much? And yep, so it becomes 40. So now we have S plus 1. And then here it changes again at about 10 to the 4, let's say. Or actually, this is 10 to the 3, right? Yeah. So S plus 1,000. And what should be the order here? Wait, so 2 would make it 0. Yeah, so you need at least 3. And then here at 10 to the 6, I get another pole. Now I also need to figure out what is the kind of the factor that this needs to be multiplied by. To do that, I just basically can just pick any value of h. So let's just say I pick, let's say I pick this 10 to the negative 2. So at 10 to the negative 2, I get negative 300 decibels, which is also equal to 10 to the negative 15. So I have to get 10 to the negative 15 when I plug in 10 to the negative 2. So I have 10 to the negative 2 divided by 10 to the 9 times 10 to the 6 times k equals 10 to the negative 15. So that's going to give me that k equals 10 to the 2. So this is just 100, whatever. Does that make sense to everyone? What? Because in order to match the correct x-axis, we need to make sure that this expression matches at a point on the graph. So we got all the slopes correct, but we don't know where to put it on the y-axis. Do we put it up here? Do we put it down here? And in order to do that, we need to basically match a point. So we just basically say h of 10 to the negative 2 has to be equal to 10 to the negative 15, which is what we read from the graph. And that allows us to figure out what k is, because we can just plug in 10 to the negative 2, 10 to the negative 2, 10 to the negative 2, 10 to the negative 2. And then we can just make both sides match to figure out k. Does that make sense? So the slopes basically give us this shape, but we need to know where is it on the height. And so to do that, we just pick a point and match it. Next slide. Yeah, so this is a good example problem of what you would expect to see in an exam. So first of all, find the H omega of this circuit. Well, you have an input voltage V1 and an output voltage V2. And so this is just a simple voltage divider. So you're going to have basically V2 over V1 equals 1 over the total impedance, which is just 1 plus 1 over the square root of 2s plus 1 over the square root of 2s. Whoa. Okay. Times that by 1 over the square root of 2s. Does that make sense? So first I find the current I, which is this voltage divided by all of these impedances in series. And then to find the voltage, I just simply multiply by the impedance of the capacitor. Once we got that, okay, so that's our expression. So I can just clean this up a little bit. So I'm going to get that the V2 over V1 is actually equal to 1 over the square root of 2s plus s squared plus 1. So I just multiplied this out in the denominator to get it cleaned up. This actually turns out to be a normalized Butterworth filter. And so effectively, we just need to figure out how much we need to rescale this circuit in order to come up with the right answer. Now, what is the order of this filter? Yeah, it's second order. So it's got two non-resistive elements. Also, if you look here, it's got two poles because it's got a quadratic polynomial on the denominator. So it's a second order filter. So we know that in this formula, we have to plug in a 2. And now all we got to do is it's telling us to design a circuit with the smallest possible cutoff frequency. So this is the smallest possible cutoff frequency. They gave us omega p, they gave us A min and A max. So we just basically plug in omega p and A max here, and then we get our answer, which is basically this. And then all you have to do now is just frequency scale this circuit to get your correct filter design. Does that make sense to everyone? All right, next one. Oh, this is a cool one. So let's say you want to design a filter. Let's say you have this low pass filter that has this response. So this is the same filter as before. How do I make it have this response? Yeah, 1 over s. Yes, exactly. So how do I do that transformation? Yeah, so basically, if I were to look at the impedance of this, SL, and the impedance of this is 1 over SC. So what that's telling me is that if I want to replace every S for 1 over S, I need to replace this component with something that has an impedance S times 1 over C, and I have to replace this with something that has an impedance of L over S. And so effectively, I just need to basically replace the inductor with a capacitor, and my capacitance has to be 1 over L, so square root of 2. And I have to replace this one with an inductor, and my inductance has to be 1 over C, which is going to be 1 over the square root of 2. And this is Henry's, and this is Faraday's, this is Ohm's. And that's it. So now I have a high pass filter with this response. Okay, what else is there? Well, how about if I want something that looks like this? What do I have to do now? So in order to go from the square root of 1 plus to this, what do I have to do to omega? What do I replace it with? Yeah, so you replace omega with omega over 100. That's also known as frequency scaling. And so what we're going to do is we're going to take our circuit that we designed in the previous slide and frequency scale it by 100 in order to go from this transfer function to this transfer function. So initially we took our inductance and replaced it with a capacitor of 1 over L. Now we're gonna basically frequency scale that by dividing it by 100. And then we're doing this by dividing it by 100. So effectively, when we're designing these high pass filters, we're both doing a low to high pass conversion and a frequency scaling when we use this formula. Yeah, so there's nothing more.
So is the omega p in those formulas, is it basically just like a factor of frequency scaling?
It's something that we inherit because when we designed this, when we choose this omega, we chose omega p over omega as a transformation factor. So we took all of our designs and we frequency scaled them by omega p. And so on the way back, we have to divide by it basically, or remove it from our frequency scaling. Yeah, this is why I kept saying that you could always change this conversion factor to 1 over omega, and then you don't have to do it here because you're just kind of multiplying by omega p to later divide by omega p. Okay, so that's good. Fine, omega's whatever. Oh, shoot. All right, let's do this. 4 minutes. 40 points in 4 minutes. Okay, so I kind of already alluded to the important things here. Like you really, look, if I give you this circuit and I told you VG is equal to 5, Vs equals 2, and Vd, and I told you it's in saturation. And I also give you what Ken is, and I gave you what V threshold is. You better be able to compute ID and figure out what VDS is. Now, additionally, if I give you a circuit that looks like this, you should know everything about it. And I'll just give you another thing in the exam. In terms of analysis, there will only be NMOS enhancement mode transistors. So you need to know these two things, and then you should also need to know these IV characteristics. Whatever, triode, saturation, VGS minus V threshold equals VDS. And then for this to be activated, VGS has to be greater than V threshold. You should know that this is really VGS in the x-axis and ID, and this is VDS in the x-axis, and then this is ID. Yeah, so just know those 4 things. And then finally, I'm just not gonna even bother with this. You do need to know small signal models. There's 1 question in the exam, and you're either going to be asked to compute an R in, an R out, or a gain for a single stage amplifier circuit. So that is going to be in the final. I just think at this point, if you know how to do any of those things, you should be able to do this. So I don't see the point in like stressing you out even more. So let's just, that 1 circuit. All right, so skip. So you should study these circuits very much. Yeah, I think these are good to know. So basically figuring out the gain of this circuit, if you can do that, you should be okay. Whatever. Skip. Yeah, here's the lines that I was talking about earlier. So just remember that since this is a PMOS, for a PMOS, whenever VGS minus V threshold is greater than 0, this thing is inactivated. So for any of these, you need that VGS minus V threshold is less than 0. If this was an NMOS, it would be the opposite relationship. Okay, whatever, common source, common gain. And I think, yeah, we're out of time. Good luck on your final quiz. What else is there? Yeah. So just as a reminder, 40 points are MOS stuff. There's one small signal question. About 100 points are the new stuff, kind of frequency response up to filters. And then the remaining 60 are solving a circuit or doing some inverse Laplace. So that's kind of the breakdown of the points.
23 questions.
Yeah, because some of them are very straightforward. It's like a mix of problem solving and either you know it or you don't. So
I don't know if you've seen my email, but just whenever the next time you're available, I'm gonna do the exam.
yeah,
I know finals week is next week, so